Has anybody used any of the videos?
Not yet.
I wonder if they work. Does anybody know for a fact whether they work or not? Yeah. That's fine. I'm actually glad you're not using them. All right. That means you're not abusing them. All right. So let's go ahead and get a rolling. So we just have sort of a little bit left in chapter 1, but again, this stuff is really important, so I'm just going to do it. I'm not going to skip over anything or anything like that. So we are going to start talking about two-dimensional polar coordinates. This is part, I don't know, 7?
Yes.
Cool. And this is going to do a lot for us because a lot of the problems we're going to be working on for a little while are going to be two-dimensional problems. One is, it's nice, you can draw a picture of them and they can lay in the page. That's nice. Other things are, you know, if we're just dealing with objects whose forces are like, for instance, gravity that's just down or radially in toward the center of the Earth. That sort of thing confines itself to, that type of motion confines itself to a plane, as does if you include drag and other forces that are along the v hat or negative v hat directions. So this is going to be good for a while. Yes, we will have to then choose in the future, we have 3D problems, so we want to use spherical polar coordinates or cylindrical polar coordinates. And what we're doing today is 2D polar coordinates. So, but just as you know going forward, this will also be the convention that we use in the cylindrical coordinates for each little slice of it. Okay. All right, so this is the situation. I've got my old Cartesian coordinates, and now I'm going to start using polar coordinates, where this angle relative to the x direction will be called phi. In your previous class, it was probably called theta, but we're going to call it phi, again, because this will be a precursor to the cylindrical coordinates, and this is actually the azimuthal angle, meaning the angle that rotates around the z-axis. You know, anyway. All right.
This makes it more like, just like spherical coordinates too, correct?
Yes, the same phi is spherical as well.
That always confused me.
That's correct. So this is the phi for both of those. This is phi. That's it. All right, and so here's my vector r, and it's got a magnitude of r and a direction, phi. I'm going to run out of places if I actually label it with r, but okay. So things that we should notice is that I can, let's say that I know my vector in this coordinate system, in the polar coordinate system, and I want to express its xy components. In that case, I would note that x is just equal to, you know, I sort of make like a right angle here, and the x component would just be r cosine phi, and the y component would be r sine phi. All right? Okay. Or let's say that I knew my x, and by the way, on my figure, let me go ahead and label. So that this is my x component here, this distance here, and this is my y component here. Okay? All right. All right. So also, let's say that I knew my x and y components. I could find my polar coordinates in that r would be equal to the square root of x squared plus y squared. And phi would be the inverse tangent or arctangent of y over x. And that will give you a number that is always between negative pi over 2 and positive pi over 2. So now, or negative 90 degrees and positive 90 degrees. So now and then, if you're in either quadrant 2 or 3, you have to add 180 degrees. In this case, I see my vector is extending into quadrant 1, so I don't have to. So this is just something that is sometimes, if you're in the right if you're in quadrants 2 or 3. All right. And so when you have a vector we express our vector r. Sometimes we'll do it x in the x hat plus y in the y hat direction. But in terms of polar coordinates, the way that you write it would be that it has a magnitude r, and it is directed at the direction phi. All right? And those are as defined in the figure. Are there any questions about that? Okay, cool. All right. So the thing about this is that at my location r, maybe I have a force acting. Maybe it's like a force like this. Maybe out there's this force acting. That's some force. Now, if I want to express that force in terms of coordinates, in terms of, we've already discussed how to handle it in terms of Cartesian coordinates. But in terms of our coordinates now, I would have to say, you know what, I've got this new coordinate system. It's going to be polar coordinate system. I'm going to define my unit vector that's along the direction of r as the r hat direction. It's parallel to r, and it's outward from the origin. And I'm going to define my phi hat direction as perpendicular to r. All right? And phi hat is always the direction that the vector would move infinitesimally if I slightly increased phi. So notice that if I slightly increased phi but kept r constant, this guy would start to travel along a circle like so. And so the direction that's tangent to that circle is always the phi hat direction. All right? Okay. All right. And so then I can see, okay, now I've got this force. It's going to have an r hat component and a phi hat component. And I'd like to solve for motion in this coordinate system, potentially, using Newton's second law. Well, I wish we could just do that right now, but we got a little bit more that we have to do. All right. So a couple of things to note. One is that the r hat unit vector is always equal to the r vector divided by its magnitude. And if you don't like using magnitude of r that way, which would be just fine, you can also write that as r vector divided by magnitude of r this way. That's equivalent. All right. So this is a notation that we're going to use for all vectors, so that now and then you might have some other vector that is, say, for instance, in this case, I've got this f vector. The f hat direction would be the f vector divided by its magnitude. All right. More generally, I might have an acceleration vector somewhere. The acceleration vector's direction would be called the a hat direction. It would be equal to the acceleration vector divided by its magnitude, and so on. All right? Okay. And we can always write a vector along with that by, noting that the acceleration vector is equal to its magnitude times the a hat direction, just multiplying both sides by the magnitude of a. Are you guys all right with that? Okay, good. I think I'm still building on things, but some of us may not have seen this for 10 years or so, so I'm just going to be complete. All right. Okay. So in this case, I started thinking about this force vector. And I could write this force vector that I drew on my figure as having an r hat component, so I could call it f sub r in the r hat direction, and a theta hat component, a component along the theta hat direction. So that'd be phi. We're doing it right. And a phi hat component, so a component that's along the phi hat direction. So I call that f sub phi times phi hat. And I apologize, I did just come off teaching 240, 250, so I'm going to now and then misspeak on that. Okay. All right. So the thing about that is that the r hat and phi hat direction are different for all the different r vectors, right? It's not like the x hat is always the x hat, If I'm here, the x hat direction is that way. If I'm here, the x hat direction is that way. But if I'm down here, the r hat direction is out this way. If I'm up here, the r hat direction is out that way. So r hat depends on r. All right. So let's see. How are we going to write Newton's second in these coordinates? I guess I'll pose that as a question. Now and then we're going to have problems that can be greatly simplified by using this coordinate system, but we still have to be able to solve for motion. So we've got Newton's second, which states that the net force on an object is equal to its mass times the resulting acceleration, which is r dot dot. And again, in rectangular coordinates, this was so easy because r dot dot, so recall, from rectangular coordinates, r dot dot was just x dot dot x hat plus y dot dot y hat. That will not be the case anymore. We will not have r dot dot r hat plus phi dot dot phi hat. For many reasons, one is unit analysis, but okay. That's not going to happen. All right. What we will have is we will have r dot dot is equal to the component along r's second derivative with respect to time minus r phi dot squared in the r hat direction plus r phi dot dot plus 2r dot phi dot in the phi hat direction. So, ouch. That's what we're going to have. Now, what we need to do is derive it. So, where did that expression come from? Why don't I show you where that expression came from? All right. So, in this case, I'm going to begin by thinking, so my point, what I'm doing right now is deriving this expression, all right? So, let's remind ourselves what we're dealing with. I've got this r vector. And let's say, so this is r. And let's say that I change my r vector by an amount delta r, except I want to imagine that it's infinitesimal. So I'm going to call it dr, even though it obviously isn't infinitesimal. And as a result, I will get this vector here that is r plus dr. Are we okay with that? Yeah. Okay. So this vector has a component along the r hat direction by which it has changed. So let's go ahead and note that in this case I have dr, and it's equal to, well, you know, I've got this magnitude r here, and I've got a similar magnitude here, except it's increased by a certain amount. So that amount of increase I will call dr. That's the change in the radial component of the vector, or the change in the vector's magnitude is another way of thinking about that. And that will be times r hat, that will be this side of the triangle. All right. Now I also need to know what's this side of the triangle. All right. So I have changed my vector r to the vector r plus dr, and in doing so, the angle associated with that direction, phi, has changed by an amount, d phi. That's what that interior angle is right there. So the magnitude of this length of triangle here in the small angle limit, which is what I am doing because I have an infinitesimal angle, in fact, would just be r times d phi. Technically, it would be r times sine d phi, but small angle limit, sine d phi equals d phi. You guys buy that? All right. Does everybody buy that? Have you guys ever calculated the sine of a teeny tiny angle in radians? This only holds in radians, by the way, obviously. Are we all okay with that? Okay. All right, so then I have plus r d phi times phi hat. That's that phi hat component there. Okay? All right. So that would be how I would write that infinitesimal change in R. Now, that is fine and good because it's going to be relatable to R dot, because R dot is dr divided by infinitesimal change in time that elapsed. All right. So what I'm going to do is I'm going to, and again, your math teacher might not like this because I'm not going to talk about limits that much, but I'm going to divide the first term by dt, and I'll get dr dt in the r hat direction. And I'm going to divide the second term by dt. Really, I'm taking the time derivative of it. And I'll get d phi dt, because r over dt is, that would be silly. We're going to let the d phi be divided by the dt phi hat. All right. And so then I can write this in terms of dots as well. So r dot r hat plus r phi dot in the phi hat direction. Okay. So now I've found in polar coordinates an expression for the velocity of my particle. Hopefully you can see that there's a dot there. But that's not what I needed. I need an expression for acceleration, so I need to keep working here. All right. So in order to get acceleration, I am going to take the time derivative of this object. And I'm going to have to use my product rule. All right. So for my first term, I'm going to get r dot dot times r hat. And for my second term, I'll get plus r dot times dr hat dt. Times. You guys okay with that from the first term? All right. And then the second term, I'm going to imagine, well, I'm just going to go ahead and put parentheses there. So I'm going to work on my parentheses. So I'll get the derivative of the parentheses with respect to time times phi hat plus the parentheses times the derivative of phi hat with respect to time. All right, so my derivative of the parentheses with respect to time, again, I have to do the product rule there as well. R d 2 phi dt squared plus r, oh, I should have done that in terms of dot, sorry. It should have been r phi dot dot, okay. Plus r dot phi dot. Okay. So that's the derivative of the stuff inside of the parentheses, so that's times phi hat, plus the stuff inside the parentheses, which is r phi dot, times d phi hat dt. Ooh, ugly. Well, hopefully it'll boil down to something nicer. We know it's going to boil down to this expression. Okay. It'll be at least a little nicer than that. All right. But now we have to start thinking about what are these changes in these unit vectors. Okay. So, let's go ahead and think about that. This page is a mess. Okay. So first of all, if I think about r hat, well, let me think in terms of r vector. R vector is equal to r times r hat. Okay. And if I rearrange this, I will see that r hat, well, do I want to do that way? Hold on just a second. Oh, okay. I'm going to write that for the infinitesimal. So dr, oh, I don't like that. Hold on just a second. Dr hat. Oh yeah, dr hat is equal to dr vector. So this is a whole vector. Oh. Hold on just a minute. I'm not liking that too well. So I've got my expression for r here. If I take dr, oh, okay, yes, that's fine. And I'm going to divide by, what am I going to divide by though? dr or r? Not a big fan of the derivation that I wrote at the moment, but I think it's by r. I think it's by r. dr hat, hold on, just, I apologize for this, but it's dr. This is what I have in my notes, but it doesn't look right to me. I want to think about that. And then if I take that, I see why I like that, because that gives me d phi plus phi hat. All right, let me continue with this, and then I'll come back and see about this. We'll discuss this step in a moment. All right, so I've got dr. I'm dividing it by r. dr is infinitesimal, so divided by r, that gives me a 0 r hat. And this guy here, that gives me r divided by r gives me 1. So then I've got d phi phi hat. Oh, plus. All right, so let me see what I think about that step, though. dr hat is equal to dr. I don't like that. I think that should be a dr down there. dr hat. I mean, I think what's happening here is that if you change r hat doesn't change. It's only through changing phi that r hat would change. So I know this expression is correct. I just can't figure out why what I'm thinking is wrong. So I'll put a little star here, and we can come back and I'll tell you why it's right next time. Because it's right. I just don't know why I'm looking at this and having a brain fart, because I don't like that expression. All right. Anyway, so all right, that's fine. I don't like it, but that's okay. So now what I wanted to think about was dr hat with respect to time. So I'm going to divide by infinitesimal time, and that will give me 0 r hat plus d phi dt, which I'll call phi dot in the phi hat direction. Okay. It is right, because changes in r will not affect dr, only changes in phi will affect it. And that is the correct expression. I just don't know why I don't like it. Does anybody else not like that expression? Let me check your book and make sure that it's right. There's a lot of stuff I don't like about that. But I think it's right. It's got to be right. Because if you go from r hat from here and then you change by an amount over here, then clearly your time rate of change of r hat was your phi dot in the phi hat direction. So I agree with that. I just don't know why I don't like that one line. So give me a second to make sure that I have a correct thing here. Make sure I've got the correct result. That's correct. Okay, no, it's correct. But let me do a slightly different derivation of that. So in this figure up here, I've got, and just remember I'm spitballing here. I've got the initial r hat is sort of going out this way radially. So here's my r hat initial. And my final r hat is kind of going out this way radially. And that's r hat final. And if I line those up tail to take their difference, I've got my r initial and I've got my r final. And this opposite side here is equal to the magnitude of one vector times the sign of d phi, also known as d phi. So this guy here is definitely d phi. And his direction is definitely the positive phi hat direction. Do you guys see that? For my figure here, this direction that it's pointed is definitely the phi hat direction up there. Are you guys okay with that? I like my qualitative derivation much better than the math one. So, okay, so it must be that dr hat is equal to d phi in the phi hat direction. So I like it. I don't know why this is distasteful to me, but I like this. So I'm going to just say I don't even need that. I'm going to do it by this argument. And so if I divide by my increment of time, I get this expression. Are you guys okay with that? All right. Okay, so let's move on to the d phi hat direction. All right, we're going to make a similar, I'm going to do a similar argument for d phi hat. So I had this r initial. And in the end, let's say that I just change phi, and as a result, I get r final. Okay, now clearly I have my phi hat direction. It's slightly different. Here it's going to be tangent to that circle whose radius is there, and here it's going to be the tangent to this circle. All right, in each case they're unit vectors. So this is phi hat initial, and this is phi hat final. Okay. Again, I can also line those up tail to head. Phi hat initial, phi hat final. They both must be unit vectors. So there's my difference between my d phi hat, and I see that what it is equal to is going to be my, similarly, again, my d phi. It's just now in the minus r hat direction. So final minus initial. All right? So here's d phi hat. And I notice that it has a magnitude of 1 times the sine of d phi, which is also this angle here. So, and it is directed in the minus r hat direction. See, it's directed inward, and that is clearly in the minus r hat direction. Are you guys okay with that? All right. Okay. So I have, I think all the, oh no, I need also d phi hat dt. And that is going to be equal to phi hat in the minus r hat direction. So I'm going to put my minus sign out front. So in terms of intermediate results that I'm going to use in my previous expression here, I'm going to use this puppy, and I'm going to use this puppy. All right. And there's probably a more elegant math derivation, but I'm going to stick with my one that's based on figures. All right, so now let me go ahead and come up with one last expression for r dot dot. I'm going to go ahead and let you guys make that substitution and get that down to QED. Remembering that QED was to find this expression up here. For r dot dot. All right. Did anybody get there yet? All right, I'll give you another moment. Please get there. Okay. We're just substituting right here. This. We're going for this expression. We have this expression, and we're substituting. What is that? Okay. And this is a zero. Do my zeros look like fives? I apologize.
No.
This is a zero. And then we're substituting that. That. So make those two plugins, and you will get after algebra to that. Okay. So we're just gathering up our R hat terms together and our phi hat terms together. Is it? Give you guys another moment. Don't be shy, talk to each other. I'm going to get rid of water. So I'm going to go ahead and do the substitutions here. So I got this line here. That seemed like it was relatively straightforward, except that I had these time-ready chains of unit vectors to think about. So I figured out how those guys change. And so now I'm going to just make some substitutions. So I've got R dot dot, so R is the R component dot dot times the R hat, plus R dot times dr hat dt, which I figured out is equal to phi hat, phi dot phi hat, plus R d2 phi dt squared. Oh, I should have done phi dot. Why did I do that? Okay. Plus R dot phi dot in the phi hat direction, plus R phi dot times d phi hat dt, which I figured out was minus phi dot times R hat. So now I'm just going to gather up everything that's multiplying an R hat. So I've got an R double dot here and minus R phi dot squared.
Mine's good enough.
No, not at all. All right, and everything with a phi dot plus, I'm going to keep this one first, R phi double dot. So plus R dot phi dot, there's another one, plus another R dot phi dot. So it's plus 2 R dot phi dot, and that's multiplying phi hat. Box around it as acceleration in two-dimensional polar coordinates. I will check it as the expression I was going for, and it looks correct. Good. Okay. So this is acceleration 2D in 2D polar coordinates. Okay? All right. Great. And then we can sort of look at that and say, does it make sense? Is it right? Because it looks like a big old mess. Well, your author is clever and says, well, let's look at the situation where R doesn't change with time, where R is constant. So that's a piece of circular motion. So if r equals constant, that means you're traveling along a circular path. Maybe not constant velocity anymore, we don't have to say that. But if we do continue to travel along a circular path, then what I will have for my acceleration is I will have, well, r doesn't change with time. There is no r dot, so there's r dot 0, so r double dot is 0. So I will have r times phi dot squared in the minus r hat direction. And again here, r dot is 0 because I'm not changing my r component. So I will have plus r phi double dot in the phi hat direction. And so basically what I'm talking about here is I've got a particle that's located at this point r, and it's traveling along some sort of circular path. Doesn't have to be constant velocity, obviously it won't be. And at this point r, at that moment in time, I know that its acceleration in the radial component is minus r omega squared. That means it's got a component of acceleration that is toward the center of the circle. That's r omega squared, which is the same expression that we got just from, 2-4 introductory physics. So that's good. And then in terms of its tangential acceleration, the component of its acceleration that's along this way, I have r times omega dot, which is also known, or d omega dt, also known as alpha, in the phi hat direction. So that is that tangential acceleration, which we already knew. Tangential acceleration of a point moving along a circle is a tangential is r alpha. You guys remember that? So a tangential is r alpha. That's left over from our introductory course, as is a centripetal, meaning toward the center of the circle, is r omega squared. So the fact that I say centripetal means it's already in the minus r hat direction. It's toward the center of the circle, toward the origin in our coordinate system. All right? So our expression, in as much as we can test it with what we already know from introductory physics, is totally correct. You guys see that? Sam, do you see it? All right, cool. All right. So that's good. So I think probably what we should do next is a problem, that in this coordinate system is easiest. So we're going to do the skate park half pipe problem. So I'm going to start a new page for that. Arranged properly? Okay. All right, so I am going to do a question that relates to a skate park. So at a skate park half pipe. If I release a skateboard from rest from point P, how long does it take to return back to point P? So that says, at a skate park half pipe, if I release a skateboard from rest at point P, how long does it take to return to P? Here's my figure. That's supposed to look like a semicircle, where this is the center of the circle. And I'm going to choose a point over here to be my arbitrary point P so that my angle theta will be positive. All right, and so this will be my point P. And for instance, at point P, I'll draw my free body diagram there. I may as well. I've got my weight down, which I think your author usually just calls mg, which is fine. And then I have this normal force that's perpendicular to the surface, and since the surface is a portion of, this cross section is a portion of a circle, that means it's toward the center. And those are the only two forces active. Now, I'm going to model my skateboard as a point particle, which is sort of okay because the only rotation goes into the wheels, and we'll say they're negligible because they're small in terms of the rotational inertia. Okay, so the next thing I'm going to do is I'm going to choose my coordinate system and write my Newton's second law in terms of that. By the way, I should have noted that this is going to be my origin of my coordinate system, and this radius we'll call capital R. Okay. All right, so my net force in the r hat direction is going to be 0 because the normal force is going to cancel out the weight force. My net force in the phi hat direction. Well, my normal force has no component in the phi hat direction. And my my weight force, if I call this angle here theta. Do I want to call that theta? I think I want to call that phi. That's what I'm calling that now, phi. Is mg, my phi hat component is mg sine phi, except it's directed in the negative phi hat direction. It's directed down. So I've got, so phi is going down. So here's the angle. So because phi is a negative number going more down, this will be minus mg sine phi. Okay, good enough. So now I have to plug in for, oh, and by the way, that should have been in another place. I'm sorry, that should have just said m r phi double dot, and then I would plug in here minus mg sine phi is equal to m r phi double dot. Okay, so clearly the r component of my location vector, which at this instant is here, the r component doesn't change because the object doesn't sink into the pipe and doesn't jump out of the pipe. And my phi does change with time. All right? Okay. So I need to figure out how. So this will be my equation of motion. So I'm going to cancel out my m's on both sides, and I have r phi double dot is equal to minus g sine theta. Or sine phi, sorry. And I think I already made an error, so no, I didn't. Okay, r phi double dot. What is r phi double dot? So the phi component. All right, so I've got the r component's not changing, so r dot 0. So I'm going to plug in on this side that I've got r times phi dot dot plus 2 r dot phi dot. Except that r dot is 0, so that term is 0. And that's equal to minus g sine phi. All right, so I've got phi dot dot is equal to minus, and by the way, this r here is also the capital R, minus g over r sine phi. It's a very difficult thing to solve. I'm only going to propose that you guys solve it for the small angle limit, where I can treat sine phi as equal to phi, in which case I get phi dot dot is equal to minus g over r times phi. We've done this before, so in the interest of finishing up, so in the next couple of minutes, I will go ahead and, why don't I just tell you the answer? Phi is equal to phi initial times cosine omega t. That's the only function whose second derivative is proportional to itself with a negative constant out front. And that negative constant out front must be equal, the magnitude of that constant out front must be equal to omega squared. If I plug in and take my second derivative, it must be that omega squared is equal to g over r, so that omega is equal to square root of g over r. Okay. So when it will return to its original location is when it will return to its original value of phi. So phi here now is the function of time. It will do that when omega, the first time it will do that is when omega t becomes 2 pi. It initially had omega t of 0, and this function had a certain value, which was phi initial. It'll get back there when omega t is equal to 2 pi. That'll be the next time. Do you guys agree with that? Okay, so that later time will be when omega t is equal to 2 pi. And I'll plug in for omega, square root of g over r times that time is equal to 2 pi. And that later time will be 2 pi times the square root of r over g. And yeah, your book gave you values for g, 9.8 meters per second squared, and r, some number of meters. And you found an actual number. But this would be all that we would have to do. All right? So hopefully you guys can just sort of absorb that example, because we're going to do a lot more like it. And so we will pick up on, we won't see you Monday, so I'll see you Wednesday. And please read chapter 2. And your homework over chapter 1 will be due on Wednesday. Yeah. That's okay. I apologize for that little bit of a hiccup there. Yes, Labor Day. Have a happy Labor Day. Have a happy 3-day weekend.
I'm not gonna let my boss know that I have Labor Day off.
Oh. So will you get the whole day off?
Yeah, they usually do, because I have a night class that goes from 6 to 9.
Yeah. That's cool. It's cool that they work it out with you.
We try, but we're understaffed right now.